Picture this. You're standing on dry land somewhere in the middle of what we now call the Mediterranean Sea. The year is approximately 5.25 million years ago. You're not floating. You're standing on cracked, sun-baked earth, surrounded by a landscape so strange, so alien, that no human mind has ever truly reckoned with it. The air is thick and heavy, superheated by the crush of an atmosphere pressing down into the deepest natural depression on the surface of this planet. You're standing more than 3 kilometers below sea level, lower than the floor of the Dead Sea, lower than any human has stood on dry land in recorded history. And stretching out around you in every direction is a vast, shimmering expanse of white salt. Thousands of meters of it. An entire sea's worth of evaporated water crystallized into silence. This was the Mediterranean basin roughly 5.25 million years ago. And if you were somehow standing there watching the horizon, you might notice something at the far western edge of the world. A faint shimmer, perhaps. A sound you couldn't quite identify, low and grinding, like tectonic plates learning a new language. What you wouldn't know, what nothing alive in that basin could possibly know, is that the wall holding back the entire Atlantic Ocean had just developed its first crack. What happened next was the single largest flood in the known history of our planet. A flood so enormous that modern scientists are still arguing about the details. A flood that filled a basin the size of a continent, that deposited enough water to drown mountain ranges, that may have happened so fast that it was, in geological terms, nearly instantaneous. We're not talking about Noah's flood. We're not talking about the Black Sea flood. We're talking about something so far beyond human scale that it reshapes what the word flood even means. We're talking about the Zanclean flood, the event that created the Mediterranean Sea as we know it today. In this video, we're going to travel through time across more than 50 million years of geological history to understand how the Mediterranean Sea first disappeared, why it vanished, what the world looked like during its absence, and then, in what may have been the most violent geological event of the last 10 million years, how it came roaring back. We're going to meet the scientists who uncovered this story, follow the evidence drilled up from the seafloor, and trace the ancient canyon that still hides beneath the Strait of Gibraltar like a scar that never quite healed. We're going to ask whether ancient human cultures, separated from these events by millions of years, somehow preserved an echo of this catastrophe in their earliest myths. And we're going to explore what this vanished sea, this drowned world, this geological cataclysm means for the civilization that eventually rose on the shores of the sea that replaced it. Before we dive in, take a second to like the video and subscribe, but only if you genuinely enjoy this strange little corner of the internet, and thank you, truly, for being here. Now, let us go back to a time before the Mediterranean existed at all. To understand the Zanclean flood, you have to understand that the Mediterranean Sea is, in geological terms, a very recent thing. The sea you see on a modern map, that elegant inland body of water stretching from Gibraltar in the west to the coast of Lebanon in the east, ringed by the ancient cultures of Greece and Rome, Egypt and Carthage, is not old. Not in the way the continents are old, not in the way the ocean floors are old. The Mediterranean, as a sea filled with water and salt and life, is geologically young, but the basin it occupies is ancient beyond reckoning, and the story of that basin is the story of an entirely different ocean that has now almost completely disappeared. To find the beginning, we have to go back approximately 250 million years to a time when the continents of Earth were arranged in configurations no modern map would recognize. At that point in deep history, most of the world's landmass was gathered into one or two enormous supercontinents, Pangaea to the west, and a vast triangular ocean called the Tethys Sea occupying the space between what would eventually become Europe, Asia, and Africa. The Tethys was not a small body of water. It was a warm, shallow, tropical sea that stretched for thousands of kilometres, teeming with life, its floor accumulating the limestone and chalk deposits that would eventually, after unimaginable geological upheaval, become the Alps, the Pyrenees, the Atlas Mountains, the Himalayas, and the Zagros Range of Iran. For hundreds of millions of years, the Tethys Sea was one of the dominant features of the planet's surface. The organisms that lived and died in its warm waters, foraminifera, mollusks, coral systems of extraordinary complexity, sank to the seafloor when they perished and slowly turned to stone, layer by layer, building up the kind of geological record that scientists would one day crack open like a book and read backwards through time. The Tethys was a nursery of evolution, a crossroads of ocean currents, and a regulator of global climate for a span of time so long it is almost meaningless to try to communicate it in human terms. Then the plates began to move in earnest. The great collision of continents that defines the last 100 million years of Earth's history set the Tethys Sea on a slow path toward obliteration. Africa began to drift northward toward Europe. The Indian subcontinent, torn free from the ancient southern landmass of Gondwana, began its long journey across the Tethys toward Asia. The ocean that had once stretched unbroken from what is now the Atlantic coast of Spain all the way to Southeast Asia began to close, squeezed from both ends, its floor diving, beneath the advancing continents in enormous subduction zones. The mountains being pushed up by these collisions, the Himalayas, the Alps, were built from the limestone bones of Tethys creatures that had died in warm, shallow water, tens of millions of years before the first hominid ever walked upright. By approximately 30 million years ago, the Tethys had been reduced to a remnant. What was left of it was divided into several smaller bodies of water, and the western portion of this remnant, the part that would eventually become the Mediterranean, was a shallow, tectonically active sea connected, at various points in its history, to both the Atlantic Ocean in the west and to the older Tethyan waters in the east. Geologists call this remnant sea the Paratethys, or, in its western form, the Proto-Mediterranean, and it was a sea that was already under enormous geological pressure. The African plate was still grinding northward. The Iberian Peninsula was rotating, volcanic, arcs were rising, sedimentary basins were deepening. The landscape of the western Mediterranean region was a geologically chaotic one, full of subsiding basins, uplifting mountain ranges, and shifting coastlines that would have been unrecognizable from one geological epoch to the next. This matters enormously, because it was precisely this tectonic chaos, this collision and grinding of plates, that would eventually create the conditions for the Mediterranean to disappear. To understand how, you have to understand the choke point that controlled everything. You have to understand what the Strait of Gibraltar was, and was not, in the time before the flood. Today, the Strait of Gibraltar is a narrow passage, roughly 14 kilometres wide at its tightest point, connecting the Atlantic Ocean to the Mediterranean Sea. Ships have passed through it for thousands of years. The ancient Greeks called it the Pillars of Hercules and believed it marked the edge of the known world. But the strait as it exists today is a recent geological feature. For the period we're concerned with, the late Miocene epoch, roughly 8 to 5 million years ago, there was no Strait of Gibraltar. Instead, there were two possible connections between the Atlantic and the Mediterranean, both located on the Iberian Peninsula, one passing through what is now southern Spain and one through what is now Morocco. Geologists call these the Betic Corridor and the Riffian Corridor, and they were the lifelines of the Mediterranean, the channels through which Atlantic water flowed freely into the basin. As long as these corridors were open, the Mediterranean was just another marginal sea, a broad, warm body of seawater connected to the global ocean, its salt balance maintained by the constant inflow of Atlantic water. Life flourished in it, Whales and dolphins cruised its depths. Giant sharks, relatives of the megalodon, hunted in its blue waters. The basin was full, alive, and unremarkable in the way that all stable things are unremarkable. But underneath this calm, the tectonics were working, the mountains were rising, the corridors were narrowing. And approximately 5.5 million years ago, in what geologists call the late Miocene, the last connection between the Atlantic Ocean and the Mediterranean Sea closed. The Mediterranean was sealed. What happened next was one of the strangest and most extreme events in the geological history of this planet. The Messinian Salinity Crisis is one of those scientific terms that sounds clinical and dry until you actually think about what it means. The Messinian is an age of geological time, spanning roughly from 7.2 to 5.3 million years ago, a period named for the Sicilian city of Messina, where geologists first began to study the strange deposits left behind by this event. The Salinity Crisis is what happened when the Mediterranean was cut off from the Atlantic, and the word crisis is, if anything, an understatement. When the last Atlantic connection closed, the Mediterranean did not immediately dry up. Evaporation from a sea surface is a gradual process, and the Mediterranean basin held an enormous volume of water, more than 3.5 million cubic kilometres of it by modern estimates. But here is the key dynamic that drove the crisis. The Mediterranean loses more water to evaporation than it gains from the rivers that flow into it. Under normal conditions, with a connection to the Atlantic, this deficit is made up by the constant inflow of Atlantic water. But when that connection closed, the deficit became permanent. Every year, more water evaporated than was replaced, and every year, the sea shrank. As the sea shrank, something else happened. The water that remained became saltier. Evaporation removes only pure water. The salt stays behind. So as the Mediterranean volume decreased, the concentration of dissolved salts in the remaining water increased. This created an increasingly hostile environment for marine life. Most organisms that had lived in the Mediterranean were adapted to normal ocean salinity, roughly 35 grams of salt per litre of water. As concentrations rose above that, species began to die. The whales and dolphins were among the first to go. Large marine mammals capable of swimming and sufficiently motivated to do so, they left. Fish that could tolerate the change persisted for a while, but the window of survivability narrowed year by year, and the salt began to precipitate. When water evaporates from a saline solution, it does not simply disappear. The salts it was carrying crystallize out, falling to the bottom in layers of white mineral deposits. First to crystallize were the carbonates, the limestones and chalks. Then came the sulfates, gypsum, the soft white mineral used to make plaster of Paris, settling in vast sheets across the seafloor. And finally, when concentrations reached extreme levels, the halite began to form. Halite is table salt, sodium chloride, and it requires water to be almost completely evaporated before it begins to precipitate. The appearance of thick halite deposits in the geological record of the Mediterranean floor is one of the most striking markers of just how extreme the Messinian crisis became. These salt deposits that were laid down during the Messinian Salinity Crisis are, even by geological standards, astonishing. Drilling campaigns in the Mediterranean have recovered cores that pass through kilometres of evaporate, the collective term for minerals deposited by evaporation. In the deep basins, the total thickness of Messinian evaporates reaches 3 kilometres or more in places. That is not 3 kilometres of salt in the sense of a thin crust. That is 3 kilometres of compressed, layered mineral deposits, representing the accumulated evaporation of an entire ocean over hundreds of thousands of years. The salt deposits of the Messinian are, in total volume, equivalent to more than 70 times the current salt content of the entire world ocean. This is not a small event. This is a planetary-scale chemical disruption, and there is something profoundly unsettling about the way these deposits were formed that only becomes apparent when you think about it carefully. The Mediterranean did not simply evaporate once and leave behind a uniform crust of salt. It was more complicated and, in a strange way, more dramatic than that. There is geological evidence, from the layering patterns of the evaporates, from the presence of certain marine microfossils appearing and disappearing through the sequence, that the Mediterranean went through multiple cycles of near-complete evaporation and partial reflooding during the Messinian period. Each time, Atlantic water managed to breach the barrier at a low level, partially refilling the basin before the connection was choked off again by tectonics or sea level changes. Each partial refilling brought new marine organisms into the dying sea. Each subsequent evaporation killed most of them and left behind another layer of mineral testament to the catastrophe. The timeline of this crisis is important to understand clearly because it frames everything that follows. The Messinian Salinity Crisis began roughly 5.9 million years ago, when the Betic Corridor, the northern connection through Spain, finally closed for good. For several 100,000 years after that, the Riffian Corridor through Morocco remained open, allowing some Atlantic water to flow in. But around 5.6 million years ago, tectonic uplift in northern Morocco closed the Riffian Corridor as well. From that moment, the Mediterranean was truly isolated, and from that moment, the crisis deepened with terrifying speed. Calculations based on the depth of the basin and the rate of evaporation suggest that a fully isolated Mediterranean would lose its surface water, dropping below the threshold where evaporation from the remaining brine becomes negligible, within roughly 1,000 years. 1,000 years is, of course, an eye blink in geological time. But it is also long enough to watch the sea recede perceptibly within a human lifetime. If any creatures with the cognitive capacity to observe such things had existed, and none did at that point, they might have watched the shoreline retreating year by year, the waters thickening and whitening with salt, the great fish dying, the seabirds abandoning their feeding grounds as the living ocean turned to brine. What was left, in the deepest parts of the basin, was not a sea. It was a series of hypersaline lakes, remnant pools of water so salty that virtually nothing could live in them, surrounded by vast flats of white crystalline salt, baking under a sun that beat down with extraordinary intensity because the atmosphere over the basin was by this point compressed to something approaching sea level plus 3 kilometers, hotter, denser, more ferocious than anything the surrounding Mediterranean landscape experienced. The deep basin of the Zanclean flood was, for a period measured in hundreds of thousands of years, one of the most hostile environments on the surface of the earth. But it was not completely lifeless, and what survived in that tortured landscape is one of the most extraordinary stories in the whole history of Mediterranean ecology. Imagine the Mediterranean basin during the height of the Messinian Crisis, perhaps 5.5 million years ago, when the desiccation was at its most extreme. What you're imagining is a landscape without parallel in modern geography, and yet it echoes, faintly, distortedly, several places on Earth today. Parts of it would have resembled the Danakil Depression in Ethiopia, which sits more than 100 meters below sea level and features pools of acidic brine, fields of sulfur yellow, crystals and temperatures that regularly exceed 50 degrees Celsius. Parts of it would have resembled the Atacama Desert of Chile, where the combination of extreme aridity and high evaporation creates salt flats of geometric perfection, white and flat and lifeless to the horizon. Parts of it would have resembled the Dead Sea region of the Middle East, another below sea level basin where evaporation exceeds inflow, and the water that remains is far too salty for most life to survive. but the Mediterranean basin was vastly larger than all of these places combined, and in some portions of it the conditions would have been unlike anything on Earth today. In the deepest parts, in what is now the Tyrrhenian Sea Basin, the Ionian Basin, the Eastern Mediterranean Trench System, the floor of the dried basin sat more than 3 kilometers below the level of the surrounding continental landscape. At those depths, the atmospheric pressure would have been measurably higher than at the surrounding surface. The temperature would have been extreme. Winds funneling down the continental slopes into the basin would have descended as foehn-type winds, warming and drying as they compressed, creating heat plumes that made the lowest points of the basin almost unimaginable as habitats for anything living. And yet life persisted. It had to, because the basins did not dry out instantaneously, and because even in extreme halite depositing conditions, there are always micro-environments, the edges of the salt flats, the deltas where rivers came down from the surrounding highlands, the zones where freshwater springs bubbled up through the salt crust, where conditions were livable. The halophiles, the salt-loving microorganisms that thrive in hypersaline environments, would certainly have been present throughout the crisis. Modern hypersaline environments like the Dead Sea, though harsh, are not biologically sterile. They support communities of archaebacteria and specially adapted algae, and by implication the Messinian evaporates would have harboured similar microbial life. More dramatic, though, are the larger organisms that managed to navigate the crisis. The freshwater rivers draining into the basin from the surrounding highlands, the ancestral Rhone, the ancestral Nile, the ancient rivers of what is now Italy and Greece and Turkey, continued to flow through the crisis period, cutting deeper and deeper into the retreating salt flats as the base level of the basin dropped further and further below them. These rivers created delta environments at the basin margins, strips of relatively fresh or brackish water where fish, amphibians and freshwater invertebrates could survive even as the sea itself became unlivable. The ancestral Nile is particularly instructive in this regard. The Nile we know today flows north from equatorial Africa and discharges into the Mediterranean near Alexandria. But during the Messinian crisis, as the floor of the Mediterranean basin dropped kilometre by kilometre below sea level, the Nile did not simply stop. It followed the retreating base level downward, cutting a canyon into the bedrock of northern Egypt and Libya that was, by the end of the crisis, genuinely staggering in its dimensions. Geologists exploring the subsurface geology of the Nile Delta region in the 20th century found, buried beneath thousands of meters of later sediment, the remains of this ancient canyon, a gorge that was, at the height of the Messinian, deeper than the Grand Canyon and cut through rock types that made the geological history of the event unmistakably clear. This ancient Nile canyon, sometimes called the Io Nile, meaning Dawner Nile, is one of the most striking pieces of physical evidence for the reality of the Messinian crisis. The canyon exists. It is there, buried under the delta sediments, and it could only have been cut by a river descending to a base level thousands of meters below the current sea surface. There is no other explanation for it. Similar buried canyons, ancient river systems that followed the retreating Mediterranean floor downward during the desiccation, have been found beneath the Rhone Delta in southern France, beneath the rivers of Spain and Italy, and traced through the submarine geology of the continental shelf. Each of these buried valleys is a monument to the crisis, a record carved in stone of a world so different from our own that it is almost impossible to hold in the mind. Meanwhile, on the continental shelves surrounding the basin, and in the river systems draining into it, the terrestrial fauna of the region was undergoing its own extraordinary transformation. The lowering of the Mediterranean floor created new land bridges where there had been seaways. Islands that had previously been separated from the mainland became connected as the encircling sea retreated. Mammals could now walk across what had been open water. There is evidence in the fossil record for this kind of faunal exchange during the Messinian, animals appearing on islands where they could not previously have reached, terrestrial species colonizing new habitats as the landscape was radically redrawn by the retreating sea. There is also evidence, tantalizing and strange, for the animals that managed to colonize the exposed salt-flat margins of the drying basin. Fossil footprints, fossil bone fragments, occasional articulated skeletons have been found in the Messinian sedimentary sequences of various Mediterranean locations, evidence that the margins of the dying sea were not entirely abandoned by vertebrate life. The basin margins would have offered something that the surrounding highlands could not always provide in that period of generally warming and drying climate: water. The residual brine pools of the Messinian basin may have been undrinkable, but the rivers and springs feeding into them produced fresh water, and where fresh water existed, animals gathered. One of the most extraordinary consequences of the Messinian desiccation was its effect on the European and African faunas. With so much water locked in the salt deposits of the basin, water that had previously separated Europe from Africa as a wide sea, the land connection between the two continents was effectively re-established in parts of the Western Mediterranean. Animals from Africa could, at least in theory, reach southern Europe by walking across terrain that had previously been submerged. Animals from Europe could move southward. The fossil record of the late Miocene shows a mixing of faunal elements that is best explained by exactly this kind of connectivity during the Messinian period. This had long-lasting consequences for the evolution of both the European and African faunas, consequences that paleontologists and biogeographers are still working to fully understand. But the most dramatic consequence of the Messinian crisis was not biological. It was geological, and it was being prepared slowly and inexorably at the far western end of the basin, in the narrow gap between Europe and Africa, where the Atlas Mountains of Morocco faced the mountain ranges of southern Spain across a landscape of crumbling salt and baking rock. It was being prepared at what was not yet the Strait of Gibraltar, what was, in that moment, simply a line of low hills separating two worlds. On one side, the brine-soaked ruins of the Mediterranean Sea. On the other side, the full Atlantic Ocean, cold and deep and vast, pressing against the barrier with every tide. The Atlantic Ocean is not a passive body of water. Like all oceans, it is in constant motion, driven by temperature gradients, wind patterns, the rotation of the Earth, and the gravitational pull of the Moon and Sun acting on its surface as tides. It has currents of tremendous power, like the Gulf Stream, which carries warm tropical water northward along the eastern coast of North America and then across toward Europe and the British Isles. It has tides that can vary by 15 meters or more in certain coastal environments. It is, in every meaningful sense, a dynamic system, a system that pushes and pulls and surges against anything that constrains it. And throughout the Messinian Salinity Crisis, the Atlantic was pressing against the barrier at the western end of the Mediterranean basin. This barrier, the rocks and sediments and mountains that had closed the Betic and Riffian corridors and sealed off the dying sea from the living ocean, was not a simple dam of uniform material. It was a complex assemblage of different rock types, sedimentary formations, fault zones and tectonic structures, all of it under constant stress from the continued convergence of the African-European plates. Some parts of the barrier were old, hard, crystalline rock, granite and metamorphic basement that had been there for hundreds of millions of years. Other parts were younger, softer sedimentary rocks that had been uplifted relatively recently by the ongoing tectonic collision. And threading through all of it were fault systems, planes of weakness in the rock where tectonic movement had sheared and fractured the material into zones that were far less resistant to erosion than the intact rock on either side. The Atlantic's tide during the Messinian would have been lapping against the western face of this barrier every 12.5 hours, and every time it surged, it was doing work. Not enormous amounts of work in any given cycle, but consistent, relentless work, the hydraulic pressure of a vast ocean pushing against a wall of rock, probing for weaknesses, widening microscopic cracks, dissolving soluble minerals, carrying away loose sediment grain by grain. On the other side of the wall, in the desiccated basin, there was no countervailing pressure of seawater. The air pressure in the deep basin was barely above normal, certainly not enough to resist the mechanical force of the Atlantic tide. The gradient was entirely one-directional, from the Atlantic, which stood at sea level, to the Mediterranean basin, which was, in its deepest parts, more than 3 kilometers lower. The elevation difference between the Atlantic Ocean surface and the floor of the deep Mediterranean basin was, at the height of the Messinian Crisis, somewhere between 3 and 5 kilometers, depending on which part of the basin you were measuring. This is a gradient of extraordinary power. Water, given any opportunity whatsoever to flow from a high point to a low point across such a gradient, will flow. The question was not whether the Atlantic would eventually break through the barrier. Any geological analysis makes that outcome essentially inevitable. The question was when the barrier would fail, how it would fail, and how fast the water would come. The timing and mechanism of the barrier's failure is one of the most intensely debated aspects of the whole Zanclean flood event, and the scientific community has not yet reached complete consensus on it. What most researchers agree on is that the initial breach was not a catastrophic event in itself. It was likely a gradual process, perhaps spanning thousands of years, in which Atlantic water began to seep through the barrier via some combination of tectonic subsidence, erosion, and the progressive failure of one or more fault zones crossing the barrier. The first trickle of Atlantic water into the Mediterranean basin may not have looked dramatic at all. It may have been indistinguishable initially from groundwater seepage or spring activity. But here is where the physics of the situation become extraordinary. As soon as Atlantic water began to flow into the deep, low basin on the other side, it began to erode the barrier from within. Water flowing across a gradient of 3 to 5 kilometers is not gently trickling water. It is fast, turbulent, energetic water, carrying enormous amounts of erosive power. Every cubic meter of water flowing through the initial seepage channels was moving at speeds and with energetic densities that were, depending on the specific geometry of the flow, capable of eroding substantial quantities of the barrier material. And every gram of rock eroded from the barrier made the channel slightly wider, slightly deeper, which allowed more water to flow through, which eroded more rock, which widened the channel further. This kind of self-amplifying erosion feedback is well understood by hydrologists. It is the mechanism by which rivers cut canyons, by which gullies form in hillsides after heavy rain, by which dam failures propagate from initial small leaks to catastrophic breaches in hours or days. But the Mediterranean situation was operating at a scale, and with a driving gradient, that had no modern parallel. The potential energy available to drive erosion was essentially the full height difference between Atlantic sea level and the bottom of the Mediterranean basin, a column of water 3 to 5 kilometers tall pushing against an eroding channel. The scientific models that have been developed in the last 20 years to simulate the Zanclean flood event, and we will discuss these models and the scientists who built them in detail later, consistently show that once the initial seepage through the barrier had progressed to a certain threshold, the rate of channel widening and deepening would have entered an exponential growth phase. The channel that had been seeping for perhaps thousands of years would suddenly begin to widen and deepen at rates measured not in centuries but in years, and then not in years but in days. At some point in the late Miocene, roughly 5.33 million years ago, the date is constrained by several independent lines of geological evidence that we will examine shortly. The barrier at Gibraltar crossed that threshold. The drip became a trickle, the trickle became a stream, the stream became a torrent, and the torrent became something for which, honestly, our language has no adequate word. The Zanclean flood had begun. Let us walk through the early stages of this event with as much physical detail as the science allows, because the details matter. They are what transform this from an abstract geological fact into something approaching lived reality. The kind of thing that, even millions of years removed and with no human witnesses, demands to be experienced imaginatively, to be inhabited, to be felt. The initial breach of the barrier was almost certainly located somewhere in the area we now call the Strait of Gibraltar, but the exact position and orientation of the first significant channel is a matter of ongoing debate. The modern Strait of Gibraltar runs roughly east-west, connecting the Atlantic to the Alboran Sea at the western end of the Mediterranean. The seafloor of the strait, when examined with modern sonar and drill cores, reveals a complex of sedimentary structures and erosional features that tell of both the original barrier materials and the catastrophic erosion that removed much of them during the Zanclean event. Buried beneath the modern seafloor sediments is a landscape of extraordinary violence. Channels cut through bedrock, enormous erosional scarps, deposits of jumbled material that could only have been transported by water, moving at tremendous velocity. As the channel through the barrier deepened and widened, the water flowing through it would have been doing something remarkable. It would have been flowing as a waterfall, or rather as a cascade of a scale completely without modern parallel. The closest analogy on the modern Earth is perhaps the Iceland-Faroe Ridge overflow, where cold, deep water spills southward from the Nordic seas into the North Atlantic over an underwater sill, creating one of the world's largest waterfalls, though this one is entirely submerged and hidden beneath thousands of meters of ocean. But even that feature is dwarfed by what was happening at Gibraltar in the late Miocene. The Gibraltar Cascade, as the initial phase of the Zanclean flood is sometimes called in the scientific literature, was dropping water from Atlantic sea level into a basin floor that was 3 or more kilometers lower, with the driving force of the full Atlantic Ocean behind it. Picture the scene at the barrier itself. On the western Atlantic side, the ocean is calm and vast, its surface barely disturbed by the relatively small amount of water being drawn down into the developing breach. The surface of the Atlantic shows only the normal patterns of swells and currents. There is nothing in the visual appearance of the water to suggest that anything unusual is happening, though an observer with instruments might notice that the tide was running consistently into the breach, rather than oscillating with the normal tidal pattern. Below the water surface, though, along the floor and lower walls of the developing channel, the situation would be anything but calm. The water here would be moving at velocities that challenge the engineering concepts of the 21st century. Water jets of extraordinary speed scouring the channel walls, creating turbulent flows of enormous power, carrying away rock fragments the size of houses in some of the later, more energetic phases of the breach development. On the eastern side of the barrier, the first water emerging from the channel would have fallen in the early stages of the breach into the air above the basin floor, or into the shallow brine lakes that might have remained in the lowest parts of the depression. The sound of this would have been extraordinary. A waterfall dropping a kilometre or more in height produces sound that can be heard for extraordinary distances. The roar of Victoria Falls, which drops a mere 100 metres, carries for tens of kilometres under the right conditions. The Gibraltar Cascade, at its peak, was dropping water thousands of metres. The acoustic energy it released would have been felt as vibration in the rock of the surrounding highlands, heard as a constant rumble across the entire western Mediterranean basin. And the water that arrived at the basin floor was not gentle. Falling even a few hundred meters accelerates water to velocities of meters per second. Falling several kilometers, accounting for air resistance, would have produced water jets moving at tens of meters per second. Where this water struck the basin floor, initially perhaps the hardened salt crust of the Messinian evaporate deposits, the impact would have been erosively catastrophic. The salt, already fractured and weakened by millions of years of alternating wetting and drying, would have dissolved and been swept away with extraordinary speed. Beneath the salt lay softer sedimentary rocks, the accumulated sediments of the Messinian and earlier periods, and these too would have been rapidly eroded by the turbulent, fast-moving water flooding across and around them. The initial footprint of Atlantic water in the basin would have been small, a plume of fresh, cold, blue-green water spreading out from the base of the cascade across the white salt flat, a stream finding its level, cutting channels beginning to pool in the lowest points of the basin floor. This would have been, in the early stages, a strange and perhaps beautiful thing. The first clean seawater in hundreds of thousands of years spreading across the desiccated surface of what had been a dying inland sea, carrying with it the cold chemistry of the open Atlantic, the microscopic organisms of the open ocean, the beginning of a biological recolonization that would eventually restore the Mediterranean to something close to its pre-crisis condition. But the early stages did not last long. As the initial cascade eroded the barrier more deeply, the flow rate through the breach increased. And as the flow rate increased, the erosive power of the water increased as well. The relationship is non-linear, with erosive power scaling roughly with the cube of velocity, meaning that doubling the flow speed increases erosive power by a factor of 8. The feedback loop was engaged. The barrier was failing at an accelerating rate. The full Atlantic Ocean was finding its level. The scientists who have modelled this process most carefully, we will return to their work in detail later in this story, calculate that the maximum flow rate through the Gibraltar Breach at the peak of the flood was somewhere between 1 million and 10 million cubic meters of water per second. To put that in context, the Amazon River, the largest river on Earth by discharge, carries about 200,000 cubic meters per second on average. The Zanclean-Gibraltar Breach, at its peak, was flowing at somewhere between 5 and 50 times the discharge of the Amazon. Every second, through a gap in the rock, the water was coming, and it was coming fast, and there was nowhere near enough rock left in the barrier to stop it. The Zanclean flood is so far outside normal human experience that it is worth spending some time simply on the numbers, because the numbers are the only way to begin to appreciate the true scale of what happened. And even the numbers, as we will see, are themselves almost incomprehensible. The Mediterranean Sea, in its modern filled state, contains approximately 3.7 million cubic kilometers of water. Write that number out in full: 3,700,000 cubic kilometers. A cubic kilometer is a cube of water 1 kilometer on each side. A block of water that, if you imagine it as a solid, would be 1,000 meters long, 1,000 meters wide, and 1,000 meters tall. 3.5 million of those cubes, stacked end to end, would stretch more than halfway from the Earth to the Moon. That is how much water was absent from the Mediterranean basin at the height of the Messinian desiccation, and that is how much water the Zanclean flood delivered. The depth of the basin before the flood is estimated, from various geological evidence, to have been between 3 and 5 kilometers below the level of the surrounding sea. The deepest modern points in the Mediterranean, the Calypso Deep in the Ionian Sea, which reaches more than 5,000 meters, may actually represent points that were exposed and dry during the Messinian. The geometry of the basin is not a simple bowl. It is a complex of sub-basins, ridges, plateaus and trenches, each of which would have filled at different rates and perhaps at different times during the Zanclean event. The question of how fast the basin filled is one of the most fascinating and contested aspects of the whole story. Scientific estimates range from as little as several thousand years at the slow end, representing a scenario in which the initial breach through the barrier was modest and the flow rate was limited by the size of the channel, to as little as a few years at the extreme fast end, representing scenarios in which the barrier failed rapidly and catastrophically once it was breached. The most widely cited recent models tend to cluster around intermediate estimates of perhaps a few hundred to a few thousand years for the main filling event, though the initial rapid phase of barrier erosion may have taken much less time. A 2009 study published in the journal Nature, led by Daniel Garcia Castellanos and colleagues, applied sophisticated hydraulic modelling to the problem and arrived at estimates that are, to put it mildly, jaw-dropping. The model suggested that the peak flow rate through the Gibraltar Channel during the most energetic phase of the breach may have reached 10 million cubic meters per second, roughly 100 times the discharge of the Amazon. At that rate, the sea level in the Mediterranean basin would have been rising at a rate of approximately 10 meters per day in the early stages of filling, when the basin was at its deepest and the water had the greatest distance to fall, 10 meters per day. Let that sink in for a moment. In a single month, the Mediterranean would have risen 300 meters. In a year, more than 3 kilometers. The deepest parts of the basin, the floors that had been exposed to air and sun for hundreds of thousands of years, would have gone from desert to 3 kilometers deep in roughly a year if the model's peak flow rates are correct. The walls of the basin, where the shallow shelves and coastal margins of the future sea were located, would have been inundated in days. Islands that had formed in the basin during the desiccation, perhaps home to endemic species that had evolved in isolation during the crisis, would have vanished under the rising water in a matter of weeks. The geology of the basin margin shows evidence consistent with this kind of catastrophically rapid inundation. In several locations around the Mediterranean coast, geologists have found what are called transgressive sequences in the rock record, layers of marine sediment sitting directly on top of the terrestrial or evaporitic deposits of the Messinian, with no gradual transition, no sequence of gradually deepening water environments that would be expected if the sea had risen slowly. Instead, there is an abrupt contact. Messinian desert on the bottom, deep sea on the top. This kind of contact is precisely what you would expect from an event in which the sea rose so fast that there was essentially no time for shallow water communities to establish themselves before the water deepened further. The energy released by the Zanclean flood during its most intense phase is difficult to calculate with precision, but estimates suggest it was equivalent to many thousands of times the annual energy output of all of humanity's power generation combined. The kinetic energy of 3.5 million cubic kilometers of water falling up to 5 kilometers, the potential energy stored in the elevation difference between the Atlantic and the basin floor, is a number that challenges the imagination. Some of it was dissipated as heat in the water itself. Some was absorbed by the enormous erosive work done on the barrier and the basin floor. Some was converted to sound, to seismic vibration, to the mechanical work of transporting billions of tons of sediment from the point of entry across the basin floor. The turbidity currents generated by this kind of event would have been extraordinary. Turbidity currents are underwater avalanches of dense, sediment-laden water that flow along the seafloor under the influence of gravity, and they are already among the most powerful geological agents known to science, capable of cutting submarine canyons, transporting sediment for hundreds of kilometers, and depositing enormous fans of material at the bases of continental slopes. The Zanclean flood, delivering water at rates that exceeded any normal oceanic process by orders of magnitude, would have generated turbidity currents of unprecedented scale, sweeping Messinian evaporate material and eroded basin margin sediments far across the forming sea floor. building the vast sedimentary architecture that underlies the modern Mediterranean seafloor. The salt was being buried. The evidence of the crisis was being covered over by the deep sea sediments of the new Mediterranean. The world that the Messinian had created, that alien landscape of salt desert and hypersaline lake and hot compressed air pressing down on white mineral plains, was disappearing beneath the rising water forever, or almost forever, because some of it was preserved. Some of it was locked in the rock in ways that would eventually allow scientists, armed with drilling ships and sensitive instruments, and the accumulated scientific knowledge of the 20th and 21st centuries to read what had happened and reconstruct the story. We will come to that reconstruction in its proper time, but first we should spend some time with what was lost, the creatures and the landscapes of the Messinian world that the flood extinguished, and the new world that the Atlantic Ocean built in its place. By the time the Zanclean flood began, the Mediterranean basin had been undergoing its crisis for somewhere between 1 and 2 million years. Over that span of time, the ecological communities of the basin had changed dramatically. The rich marine ecosystem of the pre-Messinian Mediterranean, an ecosystem that, in terms of diversity and biomass, was probably comparable to the modern Mediterranean or perhaps even richer, given the generally warmer global climate of the Miocene, had largely collapsed. The deep-water species were gone. The large marine mammals were gone. The fish that depended on a normal marine salinity had either died or retreated to the last remnants of survivable water near the basin margins and in the river systems. What replaced them in the marginal zones and freshwater environments of the drying basin was an extraordinary collection of ecological refugees, species that had originally been marine but had, over generations of adaptation, moved into fresher waters as the sea retreated, endemic species that had evolved in the isolation of river systems and coastal lakes during the crisis, and terrestrial animals that had colonized the exposed basin margins as they dried. The fish fauna of the Messinian basin is particularly fascinating. In the river systems draining into the basin, there were large communities of freshwater fish, cyprinids, the family that includes carps and minnows, perch-like species, and various other groups that had adapted to the reduced salinity environments of the basin margins over the course of the crisis. These fish were not the same as the marine species that had dominated before the crisis. They were their own evolutionary products of the Messinian isolation. When the flood came, most of them would not have survived the rapid influx of full salinity Atlantic seawater, which would have been as toxic to freshwater fish as full saltwater is to freshwater organisms today. The freshwater fish of the Messinian basin were, in effect, doomed by the very event that ended the crisis they had adapted to survive. Some of them, however, may have escaped. The rivers draining into the basin continued to flow throughout the crisis and throughout the flood, and fish populations in the upper reaches of these rivers, above the zone of marine influence, would have been insulated from the saltwater intrusion. Whether any distinctively Messinian fish lineages survived the flood in this way and went on to found modern freshwater fish populations is a question that molecular phylogenetic studies of Mediterranean freshwater fish are slowly beginning to address. The preliminary evidence suggests that yes, some modern Mediterranean freshwater fish have evolutionary lineages that trace back to the crisis period, carrying in their DNA the molecular signatures of a crisis that ended more than 5 million years ago. The terrestrial fauna of the basin margins during the Messinian is known primarily from fossil material recovered from sediments of the correct age in locations around the Mediterranean coast, and it reflects the extraordinary ecological transformation that the crisis had wrought on the landscape. The reduced sea level had created land bridges that connected previously isolated land masses, most notably the land bridge between Europe and Africa across what had been the Western Mediterranean Seaway. This land bridge allowed the exchange of faunal elements between the two continents on a scale that had not been possible for millions of years previously. Among the animals that crossed this land bridge, the fossil record shows, were several lineages of large mammals whose modern descendants are found in unexpected places. Hippopotamuses, for example, were present in Europe during the late Miocene, and some paleontologists attribute this European presence partly to the terrestrial connections created by the Messinian basin lowering. Proboscideans, elephants, and their relatives show similar patterns of intercontinental distribution during this period that are most parsimoniously explained by the existence of land connections across what is now the Mediterranean seafloor. The strange endemic dwarfism seen in island-dwelling mammals throughout the Mediterranean, dwarf elephants on Cyprus and Sicily and Sardinia, dwarf hippos on Cyprus and Malta, dwarf deer on Corsica and other islands, is a consequence of the isolation created when these populations were stranded on the elevated portions of the basin floor that remained as islands after the Zanclean flood refilled the basin around them. This last point is extraordinary when you think through its implications. The dwarf elephants of the Mediterranean islands, whose fossil bones have been found on Cyprus, Malta, Sicily, Sardinia, Crete, and several other islands, and which represent some of the most charming and unusual animals in the fossil record of the Cenozoic, were the descendants of normal-sized proboscideans that had walked or swum to what were then continental extensions or larger landmasses during the Messinian Crisis, only to find themselves stranded on islands when the Zanclean flood refilled the basin around them. Isolated on these islands, cut off from mainland gene pools, these populations underwent the classic island dwarfism process, the evolutionary reduction in body size that occurs when large animals are isolated on small islands with limited resources, and eventually produce species of elephant and hippopotamus that were no larger than large dogs. Some of these dwarf species survived for millions of years after the Zanclean flood, having adapted successfully to island life. The last dwarf hippos and dwarf elephants of the Mediterranean islands did not go extinct until human colonization of those islands, in the Holocene, within the last 10,000 years. This means that the human inhabitants of the ancient Mediterranean world, or the people of the Bronze Age, the Neolithic, the Mesolithic, encountered these strange miniature animals on the islands they colonized. What they made of them is something we can only guess at, but it is entirely possible that the traditions and mythologies of the early Mediterranean world incorporated these creatures in ways that later, in the deep compression of oral tradition across millennia, became the basis for legends about giants or monsters. The bones of a dwarf elephant, after all, might look to an untrained eye like the skull of a giant or a cyclops. But we're getting ahead of ourselves. Let us return to the flood itself and to what it created, the new Mediterranean Sea. As the Atlantic water flooded into the Mediterranean basin, it was not simply filling an empty container with seawater, it was creating a new world from the physical and chemical raw materials of the old one, and the process of that creation was attended by phenomena that, if any conscious observer had been present to witness them, would have been among the most spectacular sights in the history of our planet. The first and most immediate consequence of the flooding was the dissolution of the Messinian salt deposits. Seawater is already a saline solution, of course, but it's far less concentrated than the pure halite deposits that covered large portions of the basin floor. As Atlantic water contacted these deposits, it dissolved them rapidly, the halite dissolving first, since it is highly soluble, followed more slowly by the gypsum and the carbonate minerals. The result was that the early Mediterranean, in the days and weeks and years immediately following the initial inundation, was extraordinarily, almost unimaginably salty, a brine of concentrations far higher than normal seawater, as the incoming Atlantic water dissolved the accumulated salts of hundreds of thousands of years of evaporation. This hypersaline early Mediterranean would have been, in terms of its water chemistry, closer to the residual brine of the Messinian than to the normal ocean. The density of this water, salt water is denser than fresh water, and brine is denser than salt water, meant that it would have pooled in the deepest parts of the basin, forming a stratified water column in which the densest, saltiest water lay on the bottom and progressively less concentrated water sat above it. This kind of extreme stratification, known as miromictic stratification in lakes and as dead zones in marine environments, would have suppressed the mixing of the water column, limiting the availability of oxygen to the deep water and creating anoxic conditions without oxygen, in the deepest parts of the early Mediterranean. The hypersalinity and anoxia of the earliest Mediterranean would have made it initially a poor environment for marine life. The organisms arriving with the Atlantic water, plankton, larval fish, invertebrate spores and cysts, carried in the flow, would have encountered conditions very different from those they were adapted to. Many would not have survived long in the saline, anoxic bottom waters, but the lighter, less concentrated surface waters, continuously refreshed by the incoming Atlantic flow, would have been more hospitable, and it is in these surface waters that the biological recolonization of the Mediterranean would have begun. The process of mixing and normalization of the water chemistry would have taken some time. Estimates range from thousands to tens of thousands of years for the Mediterranean to approach normal marine salinity after the Zanclean inundation. During this transition period, the sea would have been a place of unusual and perhaps unprecedented chemistry, with different zones at different depths, characterized by radically different salinity, temperature, and oxygen conditions. The organisms that were able to tolerate this variability, the opportunistic, the generalist, the robust, would have been the first to establish themselves successfully. The specialist, the delicate, the finely tuned would have had to wait. The topography of the new Mediterranean was also different from what it is today, because the flood did not simply fill the basin. It also heavily eroded and reshaped it. The enormous water velocities of the early flood phase transported and deposited billions of tons of sediment, building vast underwater fans and plains from the eroded material of the Messinian basin floor and the barrier. The delta of the Zanclean flood, the area where the main inflow channel opened up and the water spread out into the basin, would have been a zone of extraordinary deposition, with layers of coarse material, gravels, cobbles, boulders, overlain by progressively finer sediments as the energy of the flow decreased with distance from the source. This pattern of sedimentation, preserved in the submarine geology of the Western Mediterranean, is one of the key lines of evidence that scientists have used to reconstruct the event. As the basin filled, the configuration of land and sea in the Mediterranean region was being continuously redrawn. Areas that had been dry land during the Messinian, the floor of the Alboran Sea, the shallower parts of the Western Mediterranean basins, went under water. Rivers that had been cutting canyons in their descent to the deep basin floor found their base level rising toward them, their gradients decreasing, their ability to transport sediment declining, their canyons beginning to fill with marine sediment that would eventually bury them to depths of thousands of meters. Islands that had existed as peaks above the Messinian lowstand found themselves surrounded by rising water, their connections to the mainland severed, their terrestrial populations of animals cut off and left to adapt or die. And the climate of the Mediterranean region was changing as the sea refilled. The presence of a large body of water in the basin has profound effects on the regional climate. Water moderates temperature extremes, provides moisture for rainfall, generates the sea breeze patterns and weather systems that characterize the modern Mediterranean climate. The Messinian desiccation had robbed the region of all these moderating influences, creating what must have been an extraordinarily harsh, dry, hot climate in the areas immediately surrounding the basin. As the Mediterranean refilled, the climate would have gradually ameliorated, becoming progressively wetter, more moderate, more suitable for the lush woodland and scrub vegetation that characterises the modern Mediterranean climate. The transformation was not instantaneous, and the details of how the regional climate responded to the filling of the basin are still being studied using climate models and proxy data from the geological record. But the broad outlines are clear. The return of the sea brought with it the return of a more moderate, more productive, more biologically favourable climate to the lands around the basin. This climatic amelioration, combined with the new faunal exchanges made possible by the changes in the basin geometry, set the stage for the extraordinary ecological and evolutionary diversification of the Mediterranean region in the Pliocene and Pleistocene epochs that followed. The new Mediterranean was full. It was alive. It was not yet the sea of Homer and Caesar and Cleopatra. Millions of years of biological and geological evolution still separated the Zanclean Sea from the historical Mediterranean. But it was the foundation on which all of that would eventually be built. The catastrophe was over. The creation had begun. The story of how scientists pieced together the reality of the Messinian Salinity Crisis and the Zanclean flood is itself a remarkable narrative, one that spans more than a century of geological investigation, involves some of the most ambitious and technically challenging scientific expeditions ever mounted, and culminates in a scientific consensus that continues to be refined and debated to the present day. It is the story of how human curiosity, armed with modern technology, can read the geological record of events that happened millions of years before anyone was around to observe them. The first hints that something unusual had happened to the Mediterranean in the geological past came not from drilling campaigns or sophisticated geophysical surveys, but from the most prosaic kind of field geology. Geologists walking over outcrops, picking up rocks, and asking why they looked the way they did. In the region around the city of Messina in Sicily, the region that would eventually give the Messinian Age its name, 19th and early 20th century geologists had been puzzling over a set of unusual sedimentary deposits that seemed to represent a shallow, restricted marine environment quite different from the deep water deposits that lay above and below them in the stratigraphic sequence. These deposits, gypsum, dolomite, and other evaporate minerals interbedded with marine fossils, were clearly anomalous. But their true significance was not appreciated until much later. The crucial first synthesis came in 1973 from a Dutchman named Will Druger, but the concept was developed most fully by the Italian geologist Maria Cita and the American geologist Kenneth J, both of whom were involved in a revolutionary scientific project that was transforming our understanding of the deep oceans, the Deep Sea Drilling Project. The Deep Sea Drilling Project, which operated from 1968 to 1983, was one of the most ambitious scientific undertakings in the history of Earth science. It involved drilling cores from the deep seafloor of the world's oceans from a specially designed drilling ship, the Glomar Challenger, and recovering samples of sediment and rock from depth that had never previously been sampled. By examining these cores, scientists could read the history of the deep sea directly, each layer representing a moment in geological time, its chemistry and fossil content recording the conditions that prevailed when it was deposited. In 1970, the Glomar Challenger drilled a series of cores from the floor of the Mediterranean, and what came up in those cores was, to put it mildly, unexpected. The scientists aboard expected to find deep-sea sediments all the way down, the kind of fine-grained, fossil-rich oozes that accumulate in all the world's deep ocean basins. What they found instead, below a certain depth in the cores, was something very different. They found layers of gypsum. They found dolomite. They found freshwater algae fossils. They found, in the words of Kenneth J, who wrote a popular account of the discovery in his wonderful book, The Mediterranean Was a Desert, the garbage of a vanished world, proof that the Mediterranean floor now covered by 3 or 4 kilometres of seawater had once been dry land, or at least the floor of a hypersaline inland sea. Kenneth J's account of the moment when the deep-sea drilling project scientists realised what they had found is one of the great stories of 20th century science. J describes a meeting on the Glomar Challenger in which the scientists assembled to discuss the preliminary results of the Mediterranean drilling and the atmosphere as the data began to accumulate and the implications became undeniable. Here were deep-sea sediments that should not contain evaporate minerals, and yet they did. Here were freshwater fossils thousands of meters below the current sea surface, and the only way they could have gotten there was if the surface had once been much lower. Here, in short, was proof that the Mediterranean had dried up. The Messinian Salinity Crisis was not a hypothesis. It was a geological fact, written in the rock of the seafloor. The concept that J and Cita and their colleagues developed from these discoveries, the idea that the Mediterranean had been a deep, desiccated basin before the Zanclean inundation, was initially received with considerable skepticism by parts of the geological community. It seemed too extreme, too dramatic, too far outside the normal range of geological events. But the evidence was overwhelming, and as more drilling results came in from subsequent expeditions and from the successor program to the deep-sea drilling project, the ocean drilling program, the picture became clearer and clearer. The Messinian evaporates were real, they were widespread, they were thick, and they required exactly the kind of large-scale desiccation that J and his colleagues had proposed. The reconstruction of the Zanclean flood itself, as opposed to the desiccation phase, drew on a different set of evidence. The key constraint on when the flood happened came from the stratigraphic record at the boundary between Messinian and Zanclean age sediments. In cores from the Mediterranean seafloor, and in outcrops of the Right Age around the Mediterranean coast, geologists found a boundary that was, in geological terms, essentially instantaneous. Below the boundary, Messinian evaporates and terrestrial sediments. Above it, normal marine deep-sea sediments. The boundary was so sharp, and the transition so abrupt, that it could only represent a very rapid event. The kind of rapid marine transgression that the flood model predicted. Dating this boundary precisely required the application of magnetostratigraphy, a technique that uses the pattern of magnetic reversals preserved in sedimentary rocks to correlate and date geological sequences, as well as biostratigraphy, which uses the first and last appearances of fossil species to constrain ages. From the combination of these dating methods, the Messinian-Zanclean boundary has been placed at approximately 5.33 million years ago, with uncertainties of a few tens of thousands of years. This is the date most commonly cited for the Zanclean flood, the moment when the Atlantic finally overcame the barrier and began to refill the empty basin. The scientific investigation of the Zanclean flood did not end with the deep-sea drilling project. If anything, the discoveries of the 1970s opened up a research program that has only grown more sophisticated and more productive in the decades since, as new technologies, multi-beam sonar, seismic profiling, deep-sea submersibles, satellite geodesy, advanced computational modelling, have allowed scientists to probe the geological record of the event in greater detail than Kenneth J could have imagined when he was picking through the cores from the Glomar Challenger. One of the most striking modern discoveries about the Zanclean flood concerns the structure of the seafloor in and around the Strait of Gibraltar. The modern Strait of Gibraltar is, as we noted earlier, a relatively shallow body of water. The sill depth of the strait is only about 300 meters, meaning that the deepest point of the underwater ridge that the Atlantic must overflow to reach the Mediterranean is 300 meters below the surface. But geophysical surveys of the seafloor in and around the strait have revealed something extraordinary lurking beneath the modern seafloor sediments. A deeply incised channel, a buried canyon of enormous dimensions, that cuts through the bedrock of the strait and continues westward into the Atlantic and eastward into the Alboran Sea. This buried canyon, sometimes called the Zanclean Valley or the Gibraltar Incision in the scientific literature, is the direct physical record of the erosion caused by the Zanclean flood. It was cut by the billions of cubic meters of water flowing through the breach at enormous velocity, eroding the rock of the barrier with the kind of power that only catastrophic floods can generate. The canyon has been traced by seismic profiling and drilling for hundreds of kilometers, from its Atlantic origins through the barrier zone to its terminus in the deep western Mediterranean. It is in effect the scar left by the flood, the physical signature of the most powerful water flow in the geological history of the Atlantic margin. The dimensions of the buried canyon are impressive by any standard. In cross-section, it is in places several kilometers wide and more than a kilometer deep, a gash in the bedrock of the Gibraltar region that dwarfs any modern river canyon in the area. The walls of the canyon, where they can be imaged by seismic profiling, show the stepped, terraced profile characteristic of rapid incision, the kind of profile you see in rivers that are actively cutting down through resistant bedrock, leaving benches and terraces as evidence of different stages in their downcutting. The fill of the canyon above the incised bedrock surface is complex, showing multiple phases of deposition that record different stages of the flooding event and the subsequent normalization of the strait as the main flow rate decreased and the deep scouring stopped. The relationship between the modern Strait of Gibraltar and this buried canyon is a fascinating one. The modern strait is not simply the re-exposed Zanclean Canyon, it is a modified version of it, its walls partially buried by later sediments, its floor raised by the accumulation of post-Zanclean deep-sea material, its geometry adjusted by millions of years of ongoing tectonic activity since the flood. But the inherited topography of the Zanclean incision still controls, at least in part, the geometry of the modern strait, and the buried canyon remains as a kind of geological foundation on which the current water exchange between the Atlantic and Mediterranean is built. The discovery of this buried canyon has important implications beyond the purely historical. The Strait of Gibraltar is a critically important oceanographic feature in the modern world. It controls the exchange of water between the Atlantic and the Mediterranean, and this exchange has significant effects on the circulation of the entire North Atlantic Ocean. The Mediterranean is a highly evaporative basin, meaning that it exports more water vapour to the atmosphere than it receives from rain and river inflow. This means that the water flowing out of the Mediterranean at depth through the strait is saltier and denser than normal Atlantic water, and when it enters the Atlantic it sinks and spreads through the deep North Atlantic, contributing to the Atlantic meridional overturning circulation, the large-scale ocean circulation system that is responsible for much of the warmth that Western Europe enjoys. The geometry of the Gibraltar barrier, its depth, its width, its shape, is therefore not merely a historical curiosity. It determines the modern ocean circulation system, and it was shaped in its essential form by the Zanclean flood. The flood created the canyon filled and modified to become the modern strait, and the modern strait drives an ocean circulation pattern that affects the climate of hundreds of millions of people. The catastrophe of 5 million years ago is embedded in the modern world in ways that are both subtle and profound. The Garcia Castellanos study of 2009, which we mentioned earlier in the context of flow rate estimates, also produced a detailed model of the erosion dynamics of the Gibraltar breach that has been extremely influential in shaping subsequent research. Using equations describing the relationship between water flow, channel geometry, and erosion rate, Garcia Castellanos and his colleagues were able to simulate the entire sequence of events from the initial seepage to the full breach and the subsequent moderation of the flow as the basin filled and the hydraulic head driving the flow decreased. Their model suggested that the most catastrophically erosive phase of the flood, the phase in which the channel was widening and deepening most rapidly, may have lasted only a few thousand years, with the majority of the erosive work being done in a period of perhaps a few decades to centuries. This would make the Zanclean flood, in terms of the rate of geological change it produced, essentially instantaneous by geological standards. Since the Garcia Castellanos study, numerous other research groups have developed their own models and interpretations of the event, and the scientific literature on the Zanclean flood has grown substantially. New drilling campaigns in the Mediterranean and in the approaches to Gibraltar have provided additional sedimentary data. Advanced seismic profiling has refined the three-dimensional structure of the buried canyon. Geochemical analyses of the Messinian evaporate deposits have provided more precise estimates of the volume of salt deposited during the crisis, which in turn constrains estimates of the degree of desiccation. The picture that is emerging from all this work is one of a highly dynamic and complex event, with multiple phases and considerable spatial variability in not a single simple flood, but a prolonged and geologically dramatic process with a catastrophic climax. One of the most intriguing recent line of research concerns the seismic record of the Zanclean event. Large-scale water flows generate infrasound, very low-frequency sound, and also cause ground deformation that can propagate through the crust as seismic waves. While it is not possible to directly detect the seismic signature of an event that happened 5 million years ago, the study of modern analogues, such as the seismic signals produced by large glacial lake outburst floods and by submarine landslides, is providing insights into what kind of seismic record the Zanclean flood might have left. Some researchers have proposed that certain anomalous features in the deep basement structure of the Western Mediterranean may be partially attributable to the intense ground shaking associated with the most energetic phases of the flood. The science of the Zanclean flood is, in short, very much alive. It is a field where new discoveries continue to reshape our understanding of one of the most dramatic events in the geological history of our planet, and where some of the most fundamental questions — how fast did the basin fill? What exactly happened at the barrier? How did the event affect global climate? — remain vigorously debated. Here is where the story takes a turn that is admittedly more speculative, but also perhaps more human. Because one of the questions that inevitably arises when you learn about an event as dramatic as the Zanclean flood is whether any trace of it could have survived into human cultural memory. Not a direct memory, of course. The flood happened 5 million years ago, and our hominin lineage only began to diverge from that of chimpanzees roughly 6 to 7 million years ago. No human or proto-human witnessed the Zanclean flood. But there is a longer tradition to consider. The tradition that geological catastrophes, even very ancient ones, can leave echoes in myth and folklore that far outlast any direct human memory of the event. This idea, that ancient myths may sometimes encode memories of real geological events, is one that has been treated with varying degrees of seriousness by different scholars. On the skeptical side, there is the entirely reasonable concern that reading geological content into ancient myths is a methodology prone to confirmation bias. If you look hard enough at any collection of flood myths, you can find ways to connect them to almost any large water-related geological event. On the more credulous side, there are cases where the connection between myth and geology seems to be uncomfortably precise, where the physical geography described in an ancient story matches the geological record in ways that are difficult to attribute to coincidence. The flood myths of the ancient world are, of course, extraordinarily widespread. Almost every culture on Earth has some version of a story about a great flood, a catastrophic inundation of the world that destroyed much of what existed before it and created the world as it currently is. The most famous in the Western tradition is the biblical flood of Noah, but there is also the Babylonian flood of Utnapishtim in the Epic of Gilgamesh, which is older than the biblical account and may have been one of its sources, the Greek flood of Deucalion, the Hindu flood associated with Manu, the Mesoamerican flood traditions of the Maya and Aztec, the flood myths of sub-Saharan Africa, of Pacific Island cultures, of the indigenous peoples of the Americas. The universality of flood mythology is sometimes attributed to the simple fact that floods are among the most terrifying and destructive natural phenomena that human communities regularly experience. Every culture that has ever lived near a river or a coast has probably experienced floods of local significance, and the incorporation of these experiences into mythology is unremarkable. On this interpretation, flood myths are widespread not because they reflect a single global geological event, but because flooding is a universal human experience. But there is another possibility, one that has been gaining traction in recent decades with the growth of research into prehistoric coastline changes and submerged landscapes. The last ice age ended approximately 12,000 years ago, and as the great ice sheets of the Northern Hemisphere melted, global sea level rose by roughly 120 meters. This sea level rise was not uniform or instantaneous. It occurred in multiple pulses over several thousand years, and in some regions and at some times it was very rapid indeed. The flooding of vast coastal lowlands that are now submerged, the North Sea basin, the Bering Strait land bridge, the shallow shelves around the Mediterranean, the Persian Gulf, occurred during this period and within the time frame of anatomically modern human habitation. Some of these flooding events may genuinely have been dramatic enough to leave impressions in human memory and mythology. The flooding of the Black Sea, which in a scenario proposed by geologists William Ryan and Walter Pittman in 1997 may have been rapidly inundated from the Mediterranean through the Bosphorus around 7,700 years ago, has been proposed as the geological basis for the Black Sea flood myths that appear to underlie both the Gilgamesh epic and the biblical flood story. This proposal has been debated and refined extensively since Ryan and Pittman first published it, and the evidence for and against a catastrophic Black Sea flooding event continues to be evaluated. The Mediterranean itself during the early Holocene had coastlines that were substantially different from today's. The sea level was lower, the coastal plains were wider, the islands were larger. The flooding of these coastal areas as sea level rose after the last ice age would have directly affected the human communities living there, displacing populations, submerging settlements, transforming islands into shoals and peninsulas into islands. Archaeological evidence for some of this coastal displacement exists in the form of submerged prehistoric sites, settlements, stone structures, tool assemblages that have been found on the continental shelves around the Mediterranean at depths corresponding to the sea level of several thousand years ago. The Zanclean flood itself, however, is too ancient by far to have been preserved in any human cultural memory. The 5 million year gap between the event and the earliest anatomically modern humans is simply too vast. No oral tradition, however robust, no cultural transmission mechanism, however efficient, can preserve the memory of a geological event across 5 million years. The connection between the Zanclean flood and human mythology, if it exists at all, must be indirect, but there is one intriguing possible indirect connection: the landscape of the Mediterranean basin, the arrangement of mountains and valleys, the location of islands and straits, the character of coastlines and harbours, was shaped in profound ways by the Zanclean flood and by the geological processes associated with the Messinian Crisis. The limestone mountains of Greece, the salt flats of the Tunisian coastline, the deep-water basins of the Tyrrhenian and Ionian seas, the narrow passages between islands in the Aegean, all of these are the legacy, in part, of the Messinian and Zanclean events. The world that the ancient Greeks and Romans and Phoenicians and Egyptians knew and sailed and farmed and fought over was a world whose fundamental physical geography had been sculpted by events that happened millions of years before the first human being ever set eyes on it. And if the physical landscape carries the imprint of the Zanclean flood in its bones, then every culture that has ever tried to explain the origin of that landscape, the question of why the sea is where it is, why the mountains have the shapes they have, why the deep basins of the eastern Mediterranean are so deep and so inhospitable, has been, in a sense, groping toward a geological truth that it had no tools to reach. The ancient Greek myths that explain the origin of the sea, Poseidon striking the earth with his trident, the gods dividing the world among themselves, the great rivers flowing from the edge of the world, were attempts to make sense of a landscape whose true history was encoded in millions of years of geological record that the ancient Greeks had no way of reading. They were working with the effects of the Zanclean flood without knowing the cause. There is also the matter of the Pillars of Hercules, the ancient Greek myth that explains the origin of the Strait of Gibraltar, that the hero Heracles created it by pushing apart two mountains that had previously been joined, allowing the Atlantic Ocean to flow into the Mediterranean, is a remarkably accurate mythological description of what the geological record shows actually happened. Not in the time frame or the agent, of course. No demigod pushed the mountains apart and the event happened 5 million years ago rather than in the heroic age of Greek mythology. But the core physical description, a passage carved through a barrier allowing ocean water to flow into a closed basin, is essentially correct. The Pillars of Hercules myth is, in its essential structure, a geological observation. There was a barrier, it was breached, water flowed through. Whether this represents a genuine transmission of geological knowledge, a lucky coincidence, or simply the tendency of human minds to construct similar explanatory structures for similar observed phenomena, is impossible to say with certainty. But it is a remarkable convergence, and it invites a question that is ultimately unanswerable but fascinating. If the ancient Greeks had known about the Zanclean flood in anything approaching its true form, what stories would they have told? 5 million years is a long time. It is long enough for new species to evolve and old ones to go extinct. Long enough for mountain ranges to rise and erode. Long enough for the global climate to cycle through multiple ice ages and warm periods. Long enough, in short, for the Zanclean Sea, that freshly filled, still normalizing body of water that replaced the Messinian desert, to evolve, through every geological and biological stage of its development, into something that could reasonably be called the cradle of Western civilization. The Mediterranean that the ancient Greeks and Romans knew was not, of course, the same sea that the Zanclean flood created. 5 million years of ongoing geological activity had modified the basin further. Tectonic subsidence and uplift had changed the shape of the coastlines. Volcanic activity, the volcanoes of southern Italy, the volcanic islands of the Aegean and the Tyrrhenian, had added new features to the landscape. Sea level changes associated with the glacial cycles of the Pleistocene had repeatedly lowered and raised the Mediterranean shorelines, exposing and flooding the continental shelves, connecting and disconnecting islands from the mainland, periodically opening and closing the shallow Strait of Sicily that divides the Mediterranean into its eastern and western basins. Through all of these changes, the fundamental character of the Mediterranean that had been established by the Zanclean flood persisted. A semi-enclosed body of warm, moderately saline water connected to the Atlantic through the Gibraltar Strait, ringed by diverse and tectonically active coastlines, subject to a climate characterized by dry summers and mild, wet winters. This climate, what we now call the Mediterranean climate, is one of the most productive and human-friendly climates on Earth. It is warm enough for year-round agriculture in most areas, wet enough to support dense forest and scrub in the uplands, reliably benign enough to allow seafaring in favourable seasons, diverse enough in its microclimates to support an extraordinary range of plant and animal communities. It was this climate, itself a consequence of the presence of the Mediterranean Sea, and this sea itself a consequence of the Zanclean flood, that created the conditions for the extraordinary efflorescence of human civilization along the Mediterranean shores in the last 10,000 years. Neolithic farmers moving westward from Anatolia found the Mediterranean climate ideal for the crops they had domesticated in the Fertile Crescent: wheat, barley, legumes, olives, grapes. Pastoral communities in North Africa and the Middle East found the coastal strips and mountain valleys productive enough to support settled populations. Bronze Age trading networks emerged to connect the diverse resources of the different Mediterranean shores: copper from Cyprus, tin from Spain and Britain, brought down through France, grain from Egypt, silver from the Aegean, timber from Lebanon. The sea itself was the highway. Before the development of roads and railways, travel by sea was faster, cheaper, and less laborious than travel by land, and the Mediterranean, sheltered, relatively calm in the sailing seasons, dotted with islands and natural harbours, never more than a few days' sail from a coastline, was an ideal sailing environment for the kinds of small, wooden ships that Bronze Age and early Iron Age cultures were capable of building. The Phoenicians of what is now Lebanon were among the first to exploit this highway systematically, establishing trading networks and colonies that stretched from the eastern Mediterranean all the way to the Atlantic coast of Morocco and Spain. Their colony of Carthage, in what is now Tunisia, across the narrow strait from Sicily, became one of the great powers of the ancient world. The Greeks followed, colonizing the shores of the Black Sea and the western Mediterranean, founding cities in Sicily, southern Italy, which they called Magna Graecia, Greater Greece, southern France, where Massilia, now Marseille, was founded around 600 BCE, and on the coasts of Spain and Libya. Greek culture spread along the Mediterranean highways, transforming the cultures it encountered and being transformed by them. The philosophical tradition that runs from Thales and Pythagoras through Socrates, Plato and Aristotle, the tradition that through Islamic and European transmission became the foundation of Western science and philosophy, was born in the cities of the Aegean coast, in places like Miletus and Ephesus and Athens, cities that looked out over a sea whose existence was the direct consequence of the Zanclean flood. Rome's rise to dominance over the Mediterranean world was in some ways the culmination of the maritime logic of the Mediterranean basin. Roman power was ultimately a coastal and maritime power, dependent on control of the sea lanes, on the ability to move troops and supplies by ship, on the extraction of grain and other resources from fertile coastal provinces. The famous phrase, mare nostrum, our sea, that the Romans applied to the Mediterranean was not mere arrogance. It was a recognition of the centrality of the sea to Roman civilization in a way that was almost geological in its depth. The sea was theirs because their civilization had been shaped by it, fed by it, connected through it, for so long that the relationship had become definitional. Egypt's civilization too was intimately connected to the Zanclean legacy. The Nile Valley, that narrow strip of fertility in the desert, dependent on the annual flood that deposited rich silt from the interior of Africa across the floodplain, is surrounded on both sides by the Sahara, one of the most inhospitable environments on Earth. The Egyptian civilization that built the pyramids and developed one of the world's first writing systems was made possible by the Nile, but the Nile's modern course, and the delta it discharges into, was itself shaped by the Messinian Crisis. The ancient canyon of the Io Nile, buried beneath the modern delta, is the geological foundation on which the Nile's modern course is built. The Zanclean flood, by refilling the Mediterranean basin and restoring base level to the Nile's lower course, set the hydrological conditions that would eventually make possible the stable, annually flooding river system on which Egyptian civilization depended. The connection between the ancient flood and the ancient civilizations is not a direct one. There is no causal arrow running from the Zanclean event to the building of the Parthenon or the burning of Carthage. The relationship is more like that between geology and climate, and between climate and culture, an enabling condition, a background parameter that shaped the environment within which human history unfolded. But it is real, and it is profound, and it serves as a reminder that human history is never separate from natural history, that the stage on which our species has enacted its dramas is itself a product of geological processes that were operating long before the first human being drew breath. The Mediterranean that shaped the ancient world was the Zanclean Sea, grown old and modified by 5 million years of further geological and biological evolution. The Zanclean Sea was the Atlantic Ocean's gift to an empty basin. The empty basin was the Messinian Crisis's legacy. The Messinian Crisis was the consequence of tectonic forces that had been operating for tens of millions of years. And those tectonic forces were themselves the expression of the deep inner heat of the planet, the same planetary engine that had built the Tethys Sea and then destroyed it, that had assembled and dispersed the continents over billions of years, that continues to operate today, moving the plates, building mountains, opening and closing basins, reshaping the surface of the earth on timescales that dwarf anything in human experience. The Mediterranean is not an accident. It is a product of necessity, the inevitable consequence of a set of geological processes operating on a planet that obeys the laws of physics. But it is also, from a human perspective, something like a miracle, the specific body of water, with the specific climate in the specific location that created the specific conditions in which Western civilization was born. The Zanclean flood ended roughly 5.33 million years ago. The sea it created has been filling and emptying and modifying itself ever since. And yet the evidence of the event is still there, if you know where to look, buried in the sediments of the seafloor, carved into the bedrock of the strait, encoded in the molecules of the fish that swim the modern Mediterranean, written in the salt that seasons your food and the limestone that built the walls of ancient temples. When you eat a Mediterranean olive or drink wine made from Mediterranean grapes, you're consuming the fruit of plants that evolved to thrive in the Mediterranean climate, a climate that exists because the Mediterranean Sea exists, and the Mediterranean Sea exists because the Atlantic Ocean broke through the Gibraltar Barrier 5 million years ago. When you look at a photograph of the Acropolis in Athens, or the Colosseum in Rome, or the temples of Luxor, you're looking at structures built from limestone, rock made in many cases from the compressed shells of marine organisms that lived in the ancient Tethys Sea or the pre-Messinian Mediterranean. Organisms whose existence and death and lithification were themselves part of the geological story that eventually produced the Zanclean flood. The Strait of Gibraltar, when you sail through it today, as millions of people do in vessels ranging from supertankers to kayaks, you are passing through the scar of the greatest flood in the last 10 million years. The rock on either side of you, the ridges of Spain and Morocco flanking the narrow channel, are the remnants of the barrier that once sealed the Mediterranean from the Atlantic. The water flowing under your keel, the two-layered exchange of less salty Atlantic water flowing east on the surface and saltier Mediterranean water flowing west at depth. This is the modern steady-state expression of the Atlantic-Mediterranean connection that the Zanclean flood violently re-established. The gentle, regulated tidal exchange of the modern strait is the civilized successor to the cataclysmic breach of the Zanclean event. The Mediterranean seafloor, if you could drain the sea and walk across it, would show you the landscape of the Zanclean transformation in extraordinary detail. The deep basins of the Tyrrhenian, Ionian, and eastern Mediterranean are floored by kilometres of sediment deposited since the Zanclean inundation, covering the Messinian evaporates and the eroded surface of the desiccated basin. But in places, particularly on the slopes of the basin margins where sediment cover is thin, the harder rock of the Messinian landscape protrudes through the later cover, and geologists who have sampled these outcrops have recovered pieces of the Messinian world. Evaporate minerals, hard grounds formed in the baking heat of the empty basin, fragments of continental rock that were once above water and are now 3 kilometres below the sea surface. The islands of the Mediterranean are in many cases the tops of mountains that were above water even during the deepest phase of the Messinian desiccation, the high points of the basin that the flood could not quite drown. Corsica and Sardinia, the larger islands of the Aegean, Cyprus, Malta, all of these were dry land during the crisis, surrounded by the salt desert of the drying sea, connected to the surrounding continents by the lowered base level of the basin. When the Zanclean flood rose around them, they became islands. The terrestrial life on them, the plants and animals that had colonised them during the Messinian land connection periods, was cut off and set on its own evolutionary trajectory, producing the extraordinary endemic faunas and floras that make Mediterranean islands among the most interesting places in the world for evolutionary biologists. The endemic species of Mediterranean islands are, in a very real sense, living fossils of the Zanclean world. The Sardinian pica, the Cretan spiny mouse, the unique lizard species of the Greek islands, the endemic plant communities of Cyprus and Malta. These are all the descendants of organisms that were stranded on islands by the rising waters of the Zanclean flood, or by subsequent sea level changes related to the glacial cycles of the Pleistocene. They are the biological heirs of a catastrophe. Their DNA carries, buried in its molecular archaeology, the signatures of the isolation imposed by the rising sea 5 million years ago. The Zanclean flood is also relevant to an ongoing and increasingly urgent set of questions about the modern Mediterranean and its future. The Mediterranean is one of the bodies of water most sensitive to climate change on Earth. It is already warming faster than the global average, becoming more saline as evaporation increases and freshwater inputs decrease, and experiencing changes in its circulation patterns that are affecting the distribution of marine life throughout the basin. The parallels to the Messinian Salinity Crisis, a period in which the Mediterranean's water balance was disrupted and the basin became progressively more saline and hostile to life, are not lost on oceanographers. The situations are different in important ways. The modern climate disruption is happening on a timescale of decades rather than millions of years, and there is no prospect of the modern Mediterranean being cut off from the Atlantic. But the sensitivity of the Mediterranean system to changes in the balance between evaporation and inflow, which the Messinian crisis demonstrated so dramatically at geological timescales, is also relevant at human timescales. Understanding the dynamics of the Messinian and Zanclean events gives oceanographers and climate scientists a deeper understanding of what the Mediterranean can do when its physical parameters are pushed to extremes, an understanding that becomes increasingly valuable as those parameters continue to change. There is something profound in the realization that the very sea that gave birth to Western civilization is also one of the most geologically and climatically vulnerable bodies of water on Earth, that the stability and productivity that made it a cradle of human culture is the product of a precise and delicate balance of conditions that have not always prevailed and may not always prevail in the future. The Messinian crisis reminds us that the Mediterranean can fail catastrophically. The Zanclean flood reminds us that it can be restored. But the restoration took millions of years, and the geological forces that drove it, the movement of tectonic plates, the breakthrough of an ocean barrier, are not available on human timescales. The Mediterranean we know is a gift of deep time, purchased by the catastrophic dynamics of a geological system that has been operating for hundreds of millions of years. It is also, like all gifts of deep time, contingent and impermanent, a particular configuration of land and sea and climate that will eventually, on geological timescales, give way to something different. In a few million years, the ongoing convergence of Africa and Europe may close the Strait of Gibraltar again, or the continued opening of the East African Rift may create a new connection between the Indian Ocean and the Western Mediterranean that fundamentally alters the basin's character. The Mediterranean is not finished evolving, it is just pausing. It is one thing to describe the Zanclean flood as a scientific fact, to recite the dates and the volumes and the flow rates as if they were always known, as if the story of the Mediterranean's desiccation and refilling was simply waiting in the geological record to be found. It is quite another thing to appreciate the human story of how that knowledge was actually assembled, the wrong turns and the inspired leaps, the arguments between colleagues at scientific meetings, the moments of genuine intellectual shock when the data refused to fit the expected pattern and demanded a completely different explanation. Science, at its best, is a human story, and the story of how we came to understand the Zanclean flood is one of the most compelling scientific detective stories of the 20th century. Kenneth J, the Swiss-American geologist who was perhaps the most prominent early champion of the desiccation hypothesis, came to the Mediterranean drilling project with a background in deep-sea sedimentology and a talent for seeing the implications of anomalous data that many of his contemporaries lacked. Born in China in 1929, Su had studied and worked in the United States before moving to the Swiss Federal Institute of Technology in Zurich, where he built one of the world's leading groups in sedimentary geology. When the deep-sea drilling project invited him to join one of the Mediterranean drilling legs in the early 1970s, Su was already a geologist of considerable reputation, but he was not prepared for what the cause would reveal. In his popular account of the discovery, Su describes the moment when the drill core from the deep Mediterranean floor was brought to the surface and laid out on the deck of the Glomar Challenger. The scientists crowded around it, oceanographers, geologists, paleontologists, all of them expecting to see the familiar deep-sea sediment they had encountered in 100 previous drilling operations on the world's ocean floors. What they saw instead was white, not the white of foraminiferal ooze, the normal creamy white of deep-sea carbonate sediment, but a different white, crystalline, granular, unmistakably mineral, gypsum, halite, dolomite, the minerals of evaporation, the residue of a vanished sea. The first reaction of many of the scientists on board was skepticism. Deep-sea sediments do not contain evaporate minerals. Everyone knew that. The deep sea is, by definition, always submerged. There is no mechanism by which evaporation can deposit minerals on a seafloor that is permanently covered by thousands of meters of water. The conventional explanation offered by the skeptics was that the evaporates had been transported to their current deep water location by turbidity currents from the shallow margins of the basin, that they were, in other words, sediments that had originally been deposited in shallow water and then swept into the deep basin by underwater gravity flows. This was not an unreasonable hypothesis, and it allowed the skeptics to maintain the conventional picture of an always submerged Mediterranean seafloor. But Su and his colleague Maria Cita, an Italian micropaleontologist whose expertise in the fossil foraminifera of the Mediterranean sediments was unmatched, were not satisfied with this explanation. The evaporates were too widespread, too thick, and too perfectly stratified to have been transported by turbidity currents. Turbidity current deposits have a characteristic internal structure, graded bedding, where coarser material at the base grades up to finer material at the top, that was not present in the Mediterranean evaporates. The evapораtes were primary deposits, laid down in place by the direct evaporation of the water that covered them at the time of deposition. And the only way to have direct evaporation in a deep basin is if the basin is not deep, if the water has been removed and the basin floor is exposed or nearly so to the atmosphere. The logical consequence of this reasoning was almost too large to accept. The Mediterranean had dried up, not partially, not marginally. The deep basin had been essentially empty, exposed, a desert of crystallizing salt at the bottom of a continental-scale depression. The implications cascaded through the rest of the scientific problem like a wave. If the basin had been dry, what had happened to all the life in it? Where had the water gone, evaporated into the atmosphere, adding enormous quantities of water vapor and then rainfall to the global climate system? And how, eventually, had the basin refilled? There had to have been an event, a breach, a catastrophic inrush of water from somewhere outside the basin. The Atlantic was the only possible source, and the only possible pathway for Atlantic water to reach the Mediterranean was through the western end of the basin, through whatever barrier existed at what is now Gibraltar. The Zanclean flood hypothesis was born essentially from the logic of the evaporate deposits. It was not imagined and then confirmed, it was demanded by the evidence. The rocks in the cores were speaking, and what they were saying was so strange that it took considerable scientific courage to articulate it clearly, knowing that the geological establishment would be skeptical. Maria Cita's contribution to the story cannot be overstated. While Hsu provided much of the geological framework and the popular narrative, it was Cita's meticulous biostratigraphic work. Her analysis of the foraminifera fossils in the cores above and below the evaporate interval that provided some of the most powerful evidence for the reality and timing of the desiccation. Cita identified what she called the Glomar facies, a distinctive assemblage of microfossils found just above the evaporate interval in many Mediterranean cores, representing a phase of the crisis in which the remaining water in the basin was dominated by fresh water or brackish input from rivers, and was home to communities of organisms normally found in freshwater or brackish environments rather than marine ones. The Lago Mare, Italian for Lake Sea, fauna, is one of the most extraordinary features of the Messinian record, evidence that, in the final stages of the crisis before the Zanclean flood, the remnant water bodies in the Mediterranean basin were more lake than sea, their chemistry dominated by river water rather than oceanic salt. The scientific debate over the Messinian Salinity Crisis and the Zanclean flood was fierce in the 1970s and 1980s, as it should be. Science advances through argument, through the critical examination of hypotheses, through the attempt to find alternative explanations for the data, and the eventual failure of those alternatives to account for all the evidence. Every piece of evidence that Hsu and Cita and their colleagues presented was scrutinized. Every alternative explanation was explored, and one by one the alternatives were eliminated. The evaporates were primary, not transported. The desiccation was real. The flooding event had happened. The dates from magnetostratigraphy and biostratigraphy converged on a consistent picture. By the 1990s, the broad outline of the Messinian Salinity Crisis and the Zanclean flood was accepted by essentially the entire geological community, though the details of the timing, the mechanism, and the scale continued to be debated. The subsequent generation of researchers, those who came after the initial discovery and built on the foundations that Hsu and Cita had laid, pushed the science in new directions with new tools. Geophysicists applied seismic profiling to the Mediterranean seafloor and the Gibraltar region, mapping the buried canyon of the Zanclean incision in 3 dimensions. Geochemists analyzed the isotopic composition of the evaporate minerals to extract information about the temperature and chemistry of the water from which they had precipitated. Climate modelers began to ask what the desiccation of the Mediterranean would have done to the global climate. what effects the removal of a large area of warm water surface from the world ocean would have had on atmospheric circulation, on rainfall patterns, on the distribution of heat around the planet. The answers to these questions were in some cases unexpected and are still being worked out. One of the most surprising implications of the climate modelling work has been the suggestion that the Messinian desiccation may have had significant effects on global climate beyond the Mediterranean region itself. The Mediterranean is an important part of the global water cycle. It evaporates large quantities of water vapour that eventually falls as rainfall over Europe, the Middle East, and parts of Africa. If the Mediterranean were removed from the system, or if it were reduced to a small hypersaline lake with a much smaller evaporative surface area, the downstream effects on continental rainfall patterns could have been substantial. Some researchers have proposed that the Messinian desiccation may have contributed to the increasingly arid conditions in North Africa during the late Miocene, conditions that eventually transformed what had been relatively humid woodland into the modern Sahara. The connection between the drying of the Mediterranean and the greening and then the browning of the Sahara is a complex and contested one, but it illustrates how the Messinian Salinity Crisis was not a merely regional event. It was a perturbation of the global climate system with consequences that spread far beyond the basin itself. The Zanclean flood is unique in its scale and in the specific circumstances that produced it, but it is not unique in kind. The geological record of the Earth is, if you know where to look, full of examples of catastrophic floods, events in which large bodies of water were suddenly released from containment and flowed across landscapes with devastating force. Understanding these other events helps to place the Zanclean flood in context, to appreciate both what makes it extraordinary and what it shares with the general class of geological phenomena we might call outburst floods. The most extensively studied analogues to the Zanclean flood are the Missoula floods of North America, a series of catastrophic floods that occurred at the end of the last ice age, roughly 15,000 to 13,000 years ago, when a large glacially dammed lake in what is now Montana repeatedly broke through its ice dam and discharged across the Columbia Plateau of Washington state in events of extraordinary violence. The Missoula floods are well documented in the geological record of the Pacific Northwest, in the enormous scabland landscape of eastern Washington, where the floodwaters stripped away the soil and carved the bedrock into a distinctive, deeply channeled terrain that puzzled geologists for decades before the flood hypothesis was proposed and eventually accepted. The Missoula floods are also, like the Zanclean flood, a story of scientific controversy followed by eventual acceptance. The geologist J. Harlan Bretz proposed a catastrophic flood origin for the scablands in the 1920s and was initially ridiculed by the geological establishment, which at the time was wedded to the principle of uniformitarianism, the idea that geological change is always gradual rather than catastrophic. The Missoula floods were large by any normal standard. The largest individual flood events are estimated to have had discharges of perhaps 17 million cubic meters per second, comparable to the upper estimates for the Zanclean breach at Gibraltar. But they were also temporary. Each flood event lasted only days to weeks, as the lake drained rapidly and then, as the ice dam reformed, began to fill again for the next event. The Zanclean flood, by contrast, was not a temporary event. It was the permanent refilling of the Mediterranean basin, driven by the inexhaustible reservoir of the Atlantic Ocean. Once the barrier at Gibraltar failed, there was no mechanism by which it could have reformed quickly enough to stop the flood, and the flow continued until the basin was full. Another important analogue is the flooding of the Caspian Sea basin, which went through its own dramatic changes in level during the Pleistocene as climate changes altered the balance between inflow from rivers and evaporation. The Caspian today is the world's largest inland lake, a remnant of the ancient Proteithus Sea, the same body of water whose western portion eventually became the Mediterranean. During the Pleistocene, the Caspian went through episodes of extremely high water level, the Kvalinian transgression, when the Caspian rose to levels more than 50 meters above its current surface, flooding enormous areas of what is now the steppe and semi-desert of Kazakhstan and Russia, as well as episodes of very low water level when it receded to expose large areas of its current floor. These Caspian transgressions and regressions, while far less dramatic than the Zanclean flood in terms of absolute scale, represent the same basic class of phenomenon: the dramatic and relatively rapid change in the water level of an enclosed or semi-enclosed basin in response to changes in the balance of inputs and outputs, the Black Sea flooding, event proposed by Ryan and Pittman, which we mentioned briefly in the context of ancient flood myths, is perhaps the closest analogue to the Zanclean flood in terms of the basic mechanism, even though it is far smaller in scale. In the Ryan and Pittman scenario, the Black Sea was, at the end of the last ice age, a large freshwater lake whose level was significantly below that of the Mediterranean. As Mediterranean sea level rose with the melting of the ice sheets, it eventually overtopped the Bosphorus sill and began to flow into the Black Sea basin, raising its level and converting it from a freshwater lake to a saltwater sea. The Ryan and Pittman model suggests that this transition may have been rapid and dramatic, a flood rather than a gradual transgression, and that it may have displaced human communities living around the shores of the Black Sea Lake, potentially contributing to the flood myths of the ancient Near East. The Black Sea scenario has been controversial since Ryan and Pittman first published it, and subsequent research has complicated the picture considerably. Some researchers have argued that the Black Sea was not, in fact, a freshwater lake immediately before the Holocene transgression, that there had been some connection with the Mediterranean throughout the last glacial period, and that the Holocene flooding, while real, was less dramatic and more gradual than Ryan and Pittman suggested. The debate is ongoing, but regardless of how the Black Sea story ultimately resolves, the parallel with the Zanclean flood is structurally clear. A basin below sea level, a barrier or sill, an ocean on one side, a deficit on the other, and eventually a breach that allows the ocean to flow in and fill the lower basin. Further afield, there are analogues in the geological record of the Pacific. The flooding of various basins in the Western Pacific during sea level, changes associated with the glacial cycles, the inundation of the Sunda Shelf in Southeast Asia, which was dry land during the last glacial maximum and is now the shallow seafloor of the Java Sea and South China Sea, represents the same class of event at a somewhat different scale. The Sunda flooding was gradual by comparison with the Zanclean, occurring over thousands of years as sea level rose steadily after the last glacial maximum, rather than in the rapid catastrophic burst of the Zanclean event. But it was still a massive transformation of the Earth's surface, and it occurred within the time frame of modern human habitation. The people who lived on the Sunda Shelf during the last glacial maximum were anatomically modern humans, and the rising seas that eventually drowned their home landscape may well have contributed to the Southeast Asian coastal mythologies of the sea rising and the land sinking. What all of these analogues share with the Zanclean flood is the basic dynamic of a threshold event, a system in a metastable state maintained in that state by some barrier or constraint, reaching a tipping point at which the constraint fails and the system rapidly and irreversibly transitions to a new state. This kind of threshold behaviour, familiar to physicists and ecologists and climate scientists as well as geologists, is one of the most important and least intuitive features of complex systems. Systems can remain in apparently stable states for very long periods, accumulating stress and approaching thresholds slowly and almost imperceptibly, and then fail rapidly and catastrophically when the threshold is reached. The Messinian Basin was a system under stress for nearly 2 million years, gradually approaching a threshold that, when it was finally crossed at Gibraltar, produced a response that was, in geological terms, nearly instantaneous. The threshold had been reached, the system reorganized, the world changed. This dynamic, slow accumulation, rapid threshold crossing, catastrophic reorganization, is one of the central themes of geological history and of the broader history of complex systems on this planet. Ice sheets build slowly over tens of thousands of years and collapse over decades. Mass extinctions follow millions of years of gradual environmental change and then occur in timescales measured in thousands of years or less. The Zanklin flood is one of the most spectacular examples of this pattern in the geological record of the last 10 million years, but it is not an isolated phenomenon. It is part of the fabric of a dynamic, threshold-driven planet, a world that changes slowly for long periods, and then, when it changes fast. To understand the Zanklin flood is, ultimately, to understand something important about the nature of geological time and geological change, something that goes beyond the specific details of the Mediterranean basin and speaks to the general character of the Earth as a dynamic system. The stability we experience in our ordinary lives, the apparent permanence of landscapes and coastlines and the sea itself is real on human timescales, but it is contingent. It rests on a set of conditions, geological, climatological, biological, that have not always existed and will not always persist. The Zanklin flood is a reminder, written in salt and stone, that the world we know is just one configuration among many that this planet has worn, and will wear again in its long and turbulent history. There is a remarkable continuity between the ancient events we have been discussing and the texture of daily life in the modern Mediterranean world. The salt that sits in the shakers of restaurants from Barcelona to Beirut, the salt that seasons the olives pressed from groves planted in the thin soils of Greek hillsides, and the cheeses aged in the cool cellars of Italian monasteries, this salt has, in a very real sense, a Messinian pedigree. The salt deposits left behind by the evaporating Mediterranean 5.5 million years ago are not merely geological curiosities buried deep beneath the seafloor. They are part of the active geological and chemical cycle of the Mediterranean region, dissolved and redeposited by groundwater, exposed by erosion in coastal outcrops, mined in some locations for industrial use. The gypsum quarries of Sicily, where the mineral has been extracted for centuries for use in plaster and construction, are cutting into Messinian evaporate deposits. The salt flats of the Tunisian Sahel, the salt lakes of Anatolia, the crystalline salt crusts that form along the edges of the Dead Sea. All of these are, in varying degrees, connected to the Messinian legacy, either directly as exposed Messinian deposits, or indirectly as features shaped by the same dynamics of evaporation and salt concentration that drove the crisis. The deep structural basin of the Dead Sea itself, that extraordinary below-sea-level lake on the boundary between Israel, Jordan and Palestine, famous for its extreme salinity and its buoyancy, is a geological cousin of the Messinian Mediterranean, an inland basin where evaporation outpaces inflow and the water chemistry is driven to extremes. The connection between the Messinian deposits and the modern petroleum industry is also worth noting, because it is one of the most economically significant legacies of the crisis. The evaporate deposits of the Messinian, particularly the thick halite, sequences in the deep basins of the Mediterranean, serve as excellent seals for petroleum reservoirs in the subsurface geology of the region. Halite is impermeable to hydrocarbons. It prevents oil and gas from migrating upward out of the reservoir rocks in which they formed. The presence of thick Messinian salt above potential hydrocarbon-bearing formations in the deep Mediterranean basins and in the subsurface of North Africa and the Middle East has made these regions enormously prospective for oil and gas exploration. The petroleum geologists who map the subsurface of Libya and Egypt and offshore Italy and Spain are routinely working with the Messinian evaporates as a key structural element in their geological models. The legacy of the Zanclin flood is equally present in the modern oceanography of the Mediterranean. The two-layer flow through the Strait of Gibraltar, Atlantic surface water flowing in eastward at the surface, denser Mediterranean water flowing out westward at depth, is one of the most studied features of the modern ocean circulation, precisely because of its importance to the broader Atlantic circulation system. The temperature and salinity of the Mediterranean outflow water, the MOW, as oceanographers call it, can be traced for thousands of kilometres into the Atlantic, where it spreads as a distinctive water mass at intermediate depths, its chemistry still carrying the signature of the evaporative basin from which it came. This Mediterranean outflow water is not merely an interesting tracer, it plays a functional role in the Atlantic circulation by contributing to the density stratification of the deep Atlantic and by influencing the location and intensity of deep water formation in the northern Atlantic. Changes in the Mediterranean outflow, driven by changes in the Mediterranean's evaporative budget, which in turn respond to climate changes, have been detected in the deep-sea sediment record of the Atlantic and appear to correlate with some of the major climate oscillations of the Pleistocene. The Mediterranean and the Atlantic are coupled systems, and the coupling is mediated by the Strait of Gibraltar, the scar of the Zanclin flood. Understanding this coupling has become increasingly important in the context of modern climate change. The Mediterranean is warming faster than the global ocean average, and it is becoming saltier as the evaporation to precipitation balance shifts under the influence of rising temperatures and changing rainfall patterns. These changes in Mediterranean water properties will affect the Mediterranean outflow into the Atlantic, which will in turn affect the Atlantic meridional overturning circulation, the large-scale ocean current system that is responsible for much of the mild climate of Western Europe. The degree to which changes in the Mediterranean could contribute to disruption of the Atlantic circulation is a matter of active research and some scientific concern. The Messinian Salinity Crisis, in a sense, provides the ultimate end-member scenario for what happens to the Mediterranean when its water balance is severely disrupted. The sea disappears, the climate of the surrounding region becomes harsh and arid, and the feedback effects on the global climate system are substantial. No serious scientist is predicting that the modern Mediterranean will desiccate under climate change. The connection to the Atlantic through Gibraltar is far too robust for that, and the timescales of the Messinian crisis were far longer than anything contemplated in human climate projections. But the Messinian is a reminder that the Mediterranean system has tipping points, that it has behaved radically differently in the past when the conditions that maintain it were altered, and that the consequences of disrupting it extend far beyond the basin itself. The salt that crystallized in the Messinian desert, the flood that buried it under the Atlantic Ocean, the sea that formed above it, all of these are not history in the sense of something finished and done with. They are the ongoing substrate of the present. The geology is still active, the climate is still evolving, the sea is still moving through the strait that the flood carved, and the cultures that grew on the shores of that sea are still, in ways they mostly do not articulate and cannot fully see, the inheritors of a catastrophe that no human being ever witnessed. We are all, in a sense, the children of the Zanclin flood, living on the shores of a sea that exists because an ancient barrier broke and a desert was drowned. We began this journey standing on the floor of a vanished world, a salt desert 3 kilometers below the level of the surrounding ocean, baking under a sun that no sea had cooled for hundreds of thousands of years, waiting for a sound that nothing alive could yet hear, the first trickle of Atlantic water finding its way through the crumbling rock of the Gibraltar barrier. We have travelled a long road since then, through 50 million years of geological history, through the rise and fall and flooding of seas, through the evolution and extinction of entire biological communities, through the birth of the world's most influential body of water, and the civilizations that grew on its shores. What I hope stays with you from this story is not just the spectacular drama of the flood itself, though that drama is real and extraordinary, but something quieter and perhaps more important, a sense of the depth of time beneath our feet and beneath the water and beneath the histories we tell ourselves. The Mediterranean that a Phoenician sailor crossed 3,000 years ago was already ancient beyond reckoning. The Acropolis stands on limestone that was formed from the shells of creatures that died 200 million years ago. The Nile that flooded every year to bring life to Egypt was following a course carved into bedrock by geological forces that predated the existence of our species by millions of years. We are newcomers here. The geological processes that shape the stage on which we have been acting out our histories, the tectonic forces, the erosion, the flooding and drying of basins, the opening and closing of ocean gateways, were operating for hundreds of millions of years before the first human being stood upright and looked out across a landscape they could not yet name. The Mediterranean Sea is not a backdrop to human history. It is a protagonist in the much longer story of planetary history, one of whose later chapters happens to include us. The Zanclean flood is a reminder of how dramatic that planetary story can be and of how different the world is capable of being. 5 million years ago, there was no Mediterranean Sea. There was a deep, salt-encrusted desert where 3.5 million cubic kilometers of water now rest. There were animals living in that desert that no human eye has ever seen, whose fossil bones we're only now beginning to understand. There were rivers cutting canyons of extraordinary depth into rock that is now covered by thousands of meters of seawater. There was silence where now there is the sound of waves and the calls of seabirds and the engines of ships carrying the trade of nations. The transition from that world to this one was not gradual. It was not gentle. It was one of the most violent and abrupt geological transformations in the history of this planet. A flood of such scale and power that the very word flood feels insufficient. And yet, 5 million years later, the sea it created is beautiful. The limestone cliffs of Dubrovnik reflect the late afternoon sun into turquoise water. The Aegean sparkles between its islands. The narrow straits between the Italian peninsula and Sicily carry the same currents that carried Phoenician traders and Roman warships, and, in the 20th century Allied convoys, the ancient sea is alive. It is, in the deepest sense of the word, our sea. The sea that made our world, that shaped our cultures, that carries our trade and our history and our dead. Beneath it all, 3 or 4 kilometers down, covered by millions of years of sediment, the salt of the Messinian still lies. The bones of the Zanclean Canyon still cut through the bedrock of Gibraltar. The buried valleys of the Aonal still thread through the limestone of northern Egypt, marking the path of a river that once descended to a world that no longer exists. The geological record is permanent, patient, indifferent to the ephemeral dramas of the creatures that live on the surface. It is waiting, as it always has been, to be read. Thank you for spending this time here, in this strange corner of history and geology and deep time. The ocean that exists because an ancient barrier cracked and fell, the sea that made civilization, the flood that the ancient Greeks remembered, perhaps, as a god pushing apart. Mountains at the edge of the known world, sleep well wherever you are, and remember, under every sea there is a story of the desert that came before it. Under every ocean there is the memory of dry land. There is something I find myself returning to whenever I have spent time with the deep geological record of the Mediterranean, a feeling that is difficult to name precisely, but is something between awe and vertigo. It comes from holding 2 timescales in the mind simultaneously. On one hand, the timescale of human civilization, 4,000 years from the first Egyptian dynasties to the present day, the span of history that contains every war and every empire and every piece of literature and every technological invention that we consider constitutive of our identity as a species. On the other hand, the timescale of the geological event we have been discussing, 5 million years since the Zanclean flood, preceded by 2 million years of Messinian crisis, preceded by 50 million years of Tethys Sea evolution, preceded by hundreds of millions of years of continental drift and oceanic chemistry and biological evolution. The human timescale set against the geological one is like the flicker of a candle set against the full arc of the night. And yet what the geological record shows us is that the flicker matters. The 5,000 years of human civilization that have occurred on the shores of the Mediterranean have been, in their own way, as transformative of the landscape as anything the Zanclean flood produced. Not in terms of sheer physical scale, not yet, but in terms of the reorganization of biological communities, the modification of river systems, the deforestation and reforestation of hillsides, the extraction of minerals and the combustion of buried carbon. The human transformation of the Mediterranean landscape, which began in earnest with the Neolithic agricultural revolution roughly 10,000 years ago and has accelerated dramatically since the Industrial Revolution, is writing its own layer in the geological record. The layer that future geologists, if there are any, will find above all the previous ones and read as evidence of a new kind of geological force, biological intelligence acting at planetary scale. The Zanclean flood is a story about the power of physical processes operating on timescales that dwarf anything in human experience. But it is also a story about the fragility of the configurations of land and sea that make complex life possible, about how quickly, in geological terms, a stable world can become an alien one, and how a catastrophe can be the prerequisite for a creation. The Mediterranean did not always exist. For millions of years a desert lay in its place. The desert was real, and the creatures that lived on its margins were real, and the rivers cutting their canyons toward a floor that was kilometers below them were real. And then the wall broke, and the sea came, and the world that would eventually produce the Parthenon and the Colosseum, and the first libraries and the first written laws was born from the rubble of that catastrophe. The world is older than any of us can hold in our minds, and that is somehow one of the most comforting things I know.